Well, dear students, let's start our electrochemistry. See, this is very important chapter, and in chemistry, this chapter has a great importance to explain many chemical or physico-chemical properties of matter. Right? For example, suppose that iron is given in a particular oxidation state and it is asked, okay, tell whether it is stable or unstable. So with the help of knowledge of this chapter, electrochemistry, you can very easily explain whether the given ion is stable or unstable in the given set of conditions, because all of you are knowing that ion are stable only in two places. One, it is stable in what, aqueous medium, and other one, it is stable in crystal lattice, right? And in gaseous state, ions are highly what, unstable. So chemistry of aqueous system, particularly for ionic species, you can explain with the help of this chapter, right? Electrochemistry. So this is one of the most important chapter, you can say, of your subject. Okay, the major part of this chapter are electrochemical cell, its classification, construction, and working. We have to study here electrode potential and its application, Nernst equation and cell potential and its application, electrolysis, and electrolytic cell, Faraday's laws of electrolysis. There are two Faraday laws of electrolysis are there, and electrolytic conductance and conductometric titration. So these are the major part of this chapter, and in this major headings we have some small headings as well. So before start of this first part of this chapter, electrochemical cell classification and construction, a little introduction I would like to discuss here. See how the concept of this cell and electrode potential it is developed, and what part of chemistry we are using here in this, because if you will go in the detail of this chapter, you will find that major portion of the chapter is looks like a physics, because there is a transformation of energy and we are exploiting that energy for some useful work. So but what is chemistry behind this? So I would like to discuss that important point. Suppose that you have some reaction like Na gives Na plus electron. So as per one classification of chemical reactions, what you say, this reaction is called oxidation, right? Oxidation reaction, because there is a loss of electron. So oxidation reactions are those reactions in which there is a loss of electron. Similarly, if you take some other reaction like Cl minus gives what, half Cl2 plus electron. This is also oxidation reaction. Similarly, if you take Mg2 plus 2 electrons, Mg2 plus 2 electron gives Mg, right? So this is the reduction reaction, right? This is the reduction reaction. Similarly, if you take 2H plus 2 electron gives H2, this is also reduction reaction, H2 gas reduction. Similarly, H2 gas gives 2H plus 2 electrons. This is also oxidation, right? So these are oxidation reactions, and these are reduction reactions, and many more. You can write many such reactions. Are these reactions are complete reaction, or they are half reaction? So obviously, whenever a reaction is written in front of you or anywhere, and you are if you observe that electrons are present in the reaction, either left hand side or in the right hand side, never say the reaction is a complete reaction. The reaction is always a half reaction, right? So this is the method of identification of any reaction, whether it is half reaction or complete reaction. So whenever electrons are present in this form of ionic reaction, electrons are there, then the reaction is definitely half reaction. So all these reactions are example of half reaction, and since it is oxidation, so you can say these are oxidation half reaction. Oxidation half reaction. Half reaction. And these are the reduction half reaction. Reduction half reaction. So how to recognize half reaction? If there are electrons, electron or electrons in either side of the reaction, as it is written. So this is half reaction, right? Okay, sometime you may find a reaction like this. You may find a reaction like this. KMnO4 plus H2SO4 plus H2O2 gives K2SO4 plus MnSO4 plus H2O plus O2, right? Suppose that this reaction is given anywhere. So see, in this reaction, you have any electron, neither left hand side you have found any electron, not in the right hand side. So this is not a half reaction, this is a complete reaction. Complete reaction. And every complete reaction is made up of two half reactions. One is oxidation and other is reduction. Oxidation and reduction. Oxidation and reduction, right? Except one reaction, that is you can say double decomposition reaction, where the cation and anions are exchanging. Except one reaction in the whole chemistry, all reactions are oxidation and reduction reactions, right? Again listen, except double decomposition reactions, every chemical reaction, whether it is inorganic reaction or organic reaction, every reaction is a redox reaction. Whether it is biological reaction, whether it is non-biological reaction, whether it is organic, inorganic, whatsoever reaction. right? Every reaction is redox reaction, except double decomposition reactions where only cation and anion are exchanging. So this is the scope of this redox reaction. So in every chemical reaction, you will visualize like this, that okay, this complete reaction is there, so definitely some electrons were changing. Here means some electrons are lost by some species and those electrons were accepted by some other species, means there is some oxidation of not all species present in the reaction, but some of the species gets oxidized and reduced in every chemical reaction, right? So it is clear that every chemical reaction, every chemical reaction in the universe, you can say, is a redox reaction. Means complete reaction. Complete reaction means a redox reaction, except one, and that is double decomposition reaction. Okay. So see, this is a molecular form of any reaction. Normally, I mean, a non-chemist or non-chemistry person cannot visualize, okay, where is this electrons are lost and where is this electrons were gained. But being a chemistry person, you can visualize this. See, this is an ionic compound. So this will definitely will be present in the form of what? K plus and MnO4 minus in the aqueous medium. This will not exist as a whole KMnO4 always. If it will exist only in the form of KMnO4, this will not show any chemical reaction. See, this H2SO4 exists as a what? 2H plus, since it is a strong electrolyte, so 2H plus SO4 minus minus. Don't think that this H2SO4 is always exist in the form of H2SO4. H2O2, leave that, it may exist as a H plus and OH minus, but I am taking here as a molecular form. This K2SO4 exists as a 2K plus and SO4 minus minus. MnSO4 exists as a Mn2 plus and SO4 minus minus. H2O is the molecular form and O2 in a molecular form. So if you clearly observe here, you will find that here the oxygen state is -1 and here it is 0, here it is +7 of Mn and here it is +2. So you can say that Mn in MnO4 is reduced to Mn2 plus and oxygen in H2O2 is oxidized to, right? And now you can and rest of the ions are spectator ions in this reaction. There is no change with respect to that. See, sulfate is here in the left hand side, sulfate in the right hand side, as there is no change. So this is a spectator ion. Nothing nothing is going to be changed with respect to these ions. K plus is here, K plus is here, no problem. There is no change with respect to K. So that's why I'm telling you that in a complete reaction, not every atom is going to oxidize and reduce. You have to find out which atom is going to be oxidized and reduced. But definitely there will be at least one atom to be oxidized and at least one atom to be reduced. More than one atom may oxidize, more than one atom may be reduced. It is possible, but it is not possible for a complete reaction that one atom is oxidized and none of the atom is reduced. It is not possible, right? So now this molecular reaction, you can bifurcate this reaction in two parts, oxidation and reduction. Oxidation half reaction and reduction half reaction. Reduction half reaction, right? So oxidation, H2O2 is oxidized to O2 and MnO4 MnO4 minus is reduced to Mn2 plus. Right. So and rest of the species, you can say they are all they are spectator species. They are in the supporting role. They are the main actor, right, of the reaction, and rest are the supporting staff. Okay, you can compare this with I mean. So the main role here, this is species H2O2 to O2 and MnO4 minus to Mn2 plus, and all other things are here present to maintain the system electrically neutral, and all every feature of the system they will control, right? Okay, now see, now how to find out how many electrons were, changing here in this oxidation reduction process. So you can write here, you can balance here, hydrogen you can add from your side to H plus. So see here there is no charge, neutral species is there. This is also neutral, two positive charges there, so two electrons will be here. So in fact, when H2O2 is converted into O2, there is a loss of 2 electron. And now come to here, all of you are knowing ion electron method. To balance the oxygen, you have to add water. So add 4 H2O here and 8 H plus here and 5 electron here, right? 5 electron. So see, in the reduction, there is a gain of 5 electron, and in the oxidation there is a loss of 2 electrons. How is it possible that in oxidation only 2 electrons were lost, and in reduction there are 5 electrons were gained? So see, the dear students, this is the cause of the different molar ratio requirement in the reaction. Means the balancing of equation is required due to this factor only. Means we can say the electrons are playing key role in every chemical reaction. Means the electrons will determine what molar ratio of the reactant should be present in the reaction. The number of electrons lost or gained, that will determine the stoichiometry of the reaction. You cannot arbitrarily put the moles and stoichiometric moles or balancing moles in the reaction, right? So see, there should be balancing of this moles of electrons lost or gained. So how to balance this? Obviously you will change the molar ratio of the reactant and product. So what you have to do, okay, so let's see how to balance this moles of electron. So very simple, you have to multiply this equation with 5, right, and multiply this equation with 2. So what you get, see, 5 H2O2 gives 5 O2 plus 10 H plus, and here plus 10 electrons, and here 16 H plus 2 MnO4 minus plus 10 electrons will give 2 Mn2 plus 8 H2. Now see, the moles of electrons in the reduction gain 10 electrons and lost in the oxidation 10 electrons. Now the electrons are balanced. So you can now balance this equation, and you can add these equations, left hand side with left hand side, right hand side with right hand side. This electron will be cancelled out. So what you get, 2 MnO4 minus plus 16H plus 16H plus 5H2O2. 5H2O2. This will give you 2Mn2 plus 8H2O plus 5O2 plus 5O2, and here 10H plus, so 10H plus and 16H plus, so here only 6H plus will be left, so 6H plus here, right? So this is the partial, this is the balanced ionic equation. Balanced ionic equation, right? Now if you want, you can transform this here and make the coefficient of here. So KMnO4, MnO4 coefficient is 2, so you can put here 2, so you can write here 2 KMnO4 plus H2SO4 6H plus, so 3H2SO4 you can write here, 3H2SO4 plus 5H2O2 as it is, 5H2O2 gives K2SO4. There is no term of this, so as it is you can write, and this is this will be balanced, plus 2MnSO4 plus 8H2O plus 5O. Right, so this is the balance equation. So if you see here, there is no electron here, but actually electrons are involved in this reaction. When this reaction is happening inside the beaker, in actual sense there is there are electron involvement of electrons, means KMnO4 is gaining the electron here. This species is gaining the electron KMnO4, and H2O2 is losing the electron, and see, 5 moles of H2O2 is losing 10 moles of electron, so 1 mole of H2O2, accordingly you can manipulate this. So this 5 moles of H2O2 loses 10 moles of electron total, and this 2 mole is gaining 10 moles of electron. So in this balanced equation, total transfer of electron is taking place 10 moles of electron. So you can write here, and this is a it is not everywhere it is not written, and you non-chemist person cannot see this point, this number of electrons, how many electrons are exchanging in the given reaction, and this is the important feature of this chapter, right? So total you can say 10 moles of electrons, 10 moles of electrons are are exchanging in this reaction, and this 10 moles of electrons are balanced by what, 2 moles of KMnO4 and 5 moles of H2O2, right? And this 2 and 5, this is balanced by to compensate to accommodate this 10 moles of electron. So in every chemical reaction, whatsoever the stoichiometry of the reaction is, we are putting, that is somehow directly, indirectly related to the moles of electrons exchanging in the reaction, right? Now see, if you visualize this, that in a beaker you have taken this system. In a beaker you have taken this you have taken all these reagents, like if you see KMnO4, you have taken H2SO4 and H2O2, all you have taken here. So visualize this, that all these KMnO4, H2SO4 and H2O2 you have taken. So from above reference, you can visualize that this H2O2 is losing the electrons. This will provide the electron, and this KMnO4, what surrounding, if KMnO4 is there, so this KMnO4 is accepting this electron like this. So if we make an arrangement that this KMnO4 and H2SO4 we will take in one beaker and H2O2 in other beaker, and make the arrangement that whatever electrons were lost in oxidation half reaction, means from H2O2, they will transport it through electrical circuit from outside, and that will transport it to KMnO4 half reaction, means to the KMnO4. So if we make an arrangement here like this, and here we take H2O2, which is losing the electrons, and these electrons are transported to KMnO4. So is it possible that means a same reaction, the first we identify the species which is going to be oxidized and reduced, and kept them in a separate beaker, and after that make the arrangement so that circuit will close, because you have to make some arrangement for the flow of electron. So is it possible that we can exploit this electron which were lost in oxidation, and these electrons were transported through an external circuit and transported to the KMnO4, and KMnO4 will accept this electron. So in between of the path of this electron, we can do some work, because flow of electron is basically current. So we can use this electrons which were lost in oxidation process, oxidation half reaction. We can exploit that electron in the external circuit and do some work, like we can illuminate the electrical bulb, or we can do some operate some motor or some circuit. It means we can exploit this chemical reaction, chemical energy to the electrical energy. And this is the basic concept of electrochemistry, dear students. We are here exploiting the chemical reaction. We are separating the oxidation and reduction half reactions, making an arrangement so that the electrons lost in oxidation process will be transported through the external circuit, and they are transported to the KMnO4, or you can say the species which is going to be reduced, and through this transportation in the external circuit, we can do some work in the external circuit. So this is the concept behind this. So the chemical reactions are exploited in a customized manner, so that we can convert electrical energy into chemical energy into electrical energy. So this is the basic theme, and this is the definition of cell as well. Cell, what is cell? Cell basically a device used to interconvert the energy, right? It's very simple definition. So cell is a kind of machine or a kind of device which can be used to interconvert the energy. One kind of energy can be converted into other type of energy, but the basic concept is this. What is the role of chemistry here? The role of chemistry here is this. And already I have told you that except one reaction, all the reactions are what? Redox reactions. Means you can exploit any reaction, any chemical reaction, any complete chemical reaction for this generation of electricity, right? Okay, so this is the introduction, how to visualize this chapter, and your main focus should be writing of equation and finding which species is oxidized and which species is reduced there, half reaction is there or complete reaction is there. So after this you have to do some balancing of equation and identify the oxidizing species, which species is going to be oxidized and which species is going to be reduced. This is the reason why redox reaction is kept in your class 11th syllabus, right? So now first we will define cell and then its classification. So cell is a device, right, used to interconvert the energy, right, energy. This is the simple definition of a cell. Cell is a device used to interconvert or used for interconversion of energy. See, on the basis of the interconversion of energy, we have two types of cells, right? So, electrochemical cell, you can classify electrochemical cell in two parts. Voltaic cell or galvanic cell galvanic cell, and here electrolytic cell. What is the basic difference between these two? The basic difference is here in these two cells. Here the delta G for this voltaic cell at a given temperature and pressure is less than 0. But for electrolytic cell, delta G now what is the significance and what is the explanation of this? Delta G if less than 0 means the reactions are spontaneous. So all the reactions in voltaic cell or inside the galvanic cell are spontaneous. Means what? Chemical energy is converted into electrical energy. Here chemical energy or chemical reaction energy is converted into electrical energy. And here delta G is greater than 0. So if delta G is greater than 0, what is the meaning of this? The reactions are non-spontaneous, means here a chemical reaction, you can do a chemical reaction with the help of electrical energy. Means you are converting electrical energy to chemical. Right? And what is the magnitude? magnitude through which this electrical energy can be converted into chemical energy, the magnitude through which, the amount through which this is greater than 0. And here, what is the amount which can be converted into electrical energy? The magnitude through which this is less than 0. Suppose that for any galvanic cell, total delta G is minus 50 kilojoule. Suppose that minus 50 kilojoule is there. So you can maximum convert 50 kilojoule energy into the electrical energy. Means whatever electrical energy you are getting, that is equivalent to the 50 kilojoule. That's it. Means whenever a voltaic cell is working, its delta G gradually increases from the lowest value. And what will happen once delta G achieves 0 state, delta G is equal to 0, your cell reactions are under equilibrium, means no further chemical energy is converted into electrical energy. And you know what you can say, and in general terminology, what is it is called? This is called that cell discharged, battery discharged. Means once your battery discharge, cell discharge, means delta G inside your cell or battery attains the equilibrium state, means 0. This is the meaning of your normal terminology, right? So see, this voltaic cell or galvanic cell, they are further divided into two parts. One is simple voltaic cell, and other are the concentration cell. Right? Both are voltaic cell. In both the cases, delta G is less than 0, but a little difference is there. You know, like a complete reaction, every cell basically is composed of anode and cathode. Means every cell is made up of oxidation half cell and reduction half cell, right? So if anode and cathode, you can say, if anode and cathode right, means oxidation half cell, anode you can say oxidation half cell, and cathode you can say reduction half cell. This is always true, invariably true, no difference. Any kind of cell you have, anode means oxidation, cathode means reduction half cell. See, if anode and cathode are made up of different material, then this is called simple voltaic cell, right? So anode and cathode are from different material, right? From different material. For example, anode, suppose that from zinc, and cathode from copper. So this is simple voltaic cell. So this is the way how to identify that this is simple voltaic cell or this is a concentration cell. And in a concentration cell, anode and cathode anode and cathode from same material. From same material. For example, anode made up of zinc and cathode is also made up of zinc, right? So this is called concentration cell, or anode of copper and cathode also from copper. So this is concentration cell. So if anode and cathode means both the half cells, they are made up of what? Same material, same matters, chemically same matter, then it is called concentration cell. And if they are made up of different material, then it is called simple galvanic cell. And there is a difference in polarity as well. Here in voltaic cell, anode is the negative terminal of the cell and cathode is positive terminal of the cell. But in electrochemical cell, electrolytic cell, anode is positive terminal and cathode is negative terminal, right? But remember one thing, anode and cathode are not recognized by their polarity. Anode and cathode are recognized by the type of reaction taking place on that, right? So anode and cathode, here I am putting note here, note, anode and cathode, anode and cathode are independent of polarity, are independent of polarity, right? Means on the basis of polarity you cannot determine, you cannot decide anode or cathode. Anode is characterized by oxidation irrespective of the nature of the cell. Anode is characterized by oxidation and cathode is characterized by reduction, right? Anode is characterized by oxidation and cathode is characterized by reduction. So this is the simple classification of what? Electrochemical cell. Now it is clear? Okay. Now see, every cell is made up of two half cells. So any complete cell if you have taken, so basically this is made up of two half cells. One is called oxidation half cell and other one is reduction half cell. So oxidation half cell, and you always think if oxidation half cell is there, means here oxidation reaction is responsible for this half cell, and here reduction reaction, this is a reduction half cell. If you connect this oxidation half cell internal, because internal and external. This is external. So if you connect these two half cells so that circuit is complete, then the whole arrangement is called a cell. So if you know what is the requirement for a half cell, what is the requirement of a half cell, so you can make a complete cell, because two half cells, you require minimum two half cells. Okay, you can connect so many half cells in series, but minimum two half cells are required. For making cell, right? So a complete cell is required two half cells. So if you know what is the requirement for the formation of half cell, then you can make a complete cell very easily. So oxidation half cell is also called what? Anode. And reduction half cell is also called what? Cathode. So basically, anode and cathode means oxidation half cell and reduction half cell. These two required to make a complete cell. So slowly we are moving towards the construction and functioning of working of a complete galvanic cell, right? So first I am taking this galvanic cell, galvanic cell. Galvanic cell. Right? So galvanic cell is basically made up of oxidation half cell means anode and reduction half cell means cathode. Oxidation half cell and reduction half cell. And if you connect these two half cells in a particular manner, internally and externally, basically, then you will get the complete cell. And you know, electron will flow. See, electron will flow from oxidation half cell to reduction half cell in this manner. In the external circuit, electron always flow from anode to cathode in the external circuit, and in the internal circuit, electron will flow like this, right? And anode is basically in the galvanic cell. This is the negative terminal of the cell, and this is the positive terminal of the cell. So in a galvanic cell, anode is basically negative terminal, and electron will move in external circuit from oxidation half cell means from anode to cathode, and in the internal circuit, electron will move from cathode to anode in the internal circuit, and this electron movement of this electron is apparent, means not direct. In the external circuit, the electron will move directly, but here in the internal circuit, electron moves indirectly through ions. Means what is happening in internal connection of these two half cells, electron will move, but not directly. It moves indirectly. Means in internal circuit, there is a movement of ions is taking place, and through ions, electrons apparently move, and so the circuit is closed. Okay, so now it is clear. So now see what is the requirement for making a half cell. Now see the requirement for half cell. Half cell means whenever I have not specified, the half cell, then you will consider both the half cell, oxidation as well as reduction half cell. So for both, the requirement is same. The requirement is same. So half cell, so see, for making any half cell, you have first requirement. The first requirement is the rod of the material. Okay, let's see. The first requirement is the rod of the material. Rod of material of which you want to prepare the half cell. Rod of material. This is the first requirement. Second requirement is the electrolytic solution. Electrolytic solution having reversible ion with respect to rod. With respect to rod, right? So you require rod of the material means you want I mean you should have rod of the material of which you want to prepare the half cell. For example, if you want to prepare the half cell for zinc, then you must have the rod of the zinc. If you want to prepare the half cell of copper, then you have to the rod of the copper. And second one is the electrolytic solution. See, electrolytic solution. So where to make this solution? In benzene or in water? Obviously in water. So electrolytic aqueous solution. It is better to add here aqueous solution. Electrolytic aqueous solution having reversible ion with respect to rod. So this is very important keyword throughout this chapter. There must be some reversible ion with respect to rod. Suppose that if you have zinc rod, then you have to have electrolytic solution having zinc ion. Second ion, counter ion, or non-reversible ion, you can take anything. You may take chloride, you may take oxide, you may take a hydroxide. That hardly matters, right? So minimum requirement is zinc. So this is very important, and you have to focused here. This is very crucial point of this chapter. So the first requirement is rod of the material, and the second requirement is the electrolytic solution having reversible ion with respect to rod, and the third requirement is inert beaker. Inert beaker. Why I have written inert beaker? Why I have written here inert beaker? You know, if your beaker is active, then what will happen? Sometime that beaker may act as an electrode. So be extra careful in electrochemistry that if there is a, in a question there is a mention of this beaker, and that this beaker is made up of some metal like that. So you will think about this, okay, whether this beaker is not the part of our half cell reaction. So be extra careful. So as per my requirement, inert beaker should be there, because I want this rod of the material. I have taken rod of the material, so I must take the beaker inert, right? Suppose that you have taken copper sulfate in the beaker of copper, then what will happen? Obviously, the copper beaker, the material of the beaker, that acts as a rod of the material. Whatsoever I have written here, rod of the material, that it is not, it should be not like this, that only cylindrical shape of material you are accepting. So if you are taking copper sulfate in copper beaker, then what will happen? Copper may act as a electrode, because that copper will act as a rod of the material. So every time when you are making this half cell or complete cell, you have to be extra careful. Now let's see one by one example here. So is there any, I have put a restriction here that only solid can be used here, or we can use liquid. Any restriction I have not given, only I have given rod of the material. So you should ask a question. You may ask the question, sir, if I want to prepare some electrode of liquid material electrode, then what I will do? How to procure this rod of the liquid? If I want to prepare electrode of some gas, then how to prepare rod of the material? And you have told me that, okay, rod of the material is required. So one by one I will explain you, I'm going to explain here that how to make a half cell of solid, of liquid, or of gas. So first I am taking here solid. So in case of solid, I think there is no problem to anybody that you can procure this rod of the material. So first case I am taking solid. So in case of solid, there is no problem at all, and you can take the rod of the material. Rod of the material, right? So one by one example we can take. Suppose that we want this zinc half cell. So zinc half cell, if we wish to prepare zinc half cell. So for this zinc half cell, you require rod of zinc first, and you can easily get the rod of the zinc, no problem. And second requirement, now identify reversible ion with respect to zinc. So the reversible ion Zn2 plus is the reversible ion with respect to zinc. So Zn2 plus is the reversible ion with respect to zinc. So you can take any electrolytic solution having zinc. For example, you can take ZnSO4 aqueous. You can take Zn nitrate aqueous. You can take ZnOH whole twice aqueous. You can take ZnO2 minus aqueous, right? You can take any of this species as a source of Zn2 plus. So these are the source for Zn2 plus. So this you have to require it, right? How to represent this half cell? See, see, so this is the source of electrolyte, source of Zn2 plus, and these are the electrolytes you can take, right? Aqueous medium, in aqueous medium. Okay, so how to represent this half cell? See, you have to put this zinc rod in the any one of this solution, or even you can take mixture of electrolytes as well. That will not prevent you to make any, I mean, half cell. So even you can take mixture of electrolytes as well. So suppose that if you want to prepare a half cell, you should take a inert beaker. So I am taking this glass beaker, Borosel company, glass, and here we have taken this ZnSO4. So ZnSO4 aqueous will exist like this, and this zinc rod, and this is zinc sulfate solution. So this is the representation of a half cell. So this is a, I mean, diagram, and how it is represented. See, this is solid, Zn solid, and this is in contact with the liquid phase. So here you can write a interface slash like this. Zn solid and Zn2SO4. This is aqueous, right? So this is the representation of half cell. On paper we will represent this whole arrangement like this, right? This whole arrangement is represented like this. So this is the half cell representation, half cell representation. Or in a simplified manner, you may find this cell like this also, Zn solid, Zn2 plus aqueous. Because you know this Zn2 plus is the only ion which is responsible for the electrode potential or development of electrical charge. So that's why only we are talking about only reversible ions. So this is very important terminology here, and you must be aware about this and must be able to identify the reversible ion in every half cell reaction. Okay. Similarly, if you want to prepare the half cell of half cell of copper, so if you want to prepare half cell of copper, so what is the basic requirement for the half cell of copper? You want copper rod, you want electrolytic solution, electrolytic aqueous solution, So you can take copper sulfate, aqueous, copper nitrate, aqueous, copper hydroxide, aqueous. aqueous, etc. Right? So this is the electrolytic solution. So what is the reversible ion here? The reversible ion is copper 2 plus, right? So how to represent this? You can represent this copper solid, copper sulfate aqueous, or copper solid, copper 2 plus aqueous. So this is the representation of this half cell, right? So in this way you can represent these half cells. Okay, good.